area. Eyewitnesses described a column of blue light streaking across the sky before the horizon exploded. The blast released the energy of up to 50 megatons of TNT, flattening 800 square miles of forest and snapping millions of trees. This shockwave was so violent that it knocked people unconscious dozens of miles away and was recorded by seismic stations across the globe. This remains the largest impact event in recorded human history. However, its extreme isolation meant that its physical secrets would remain buried for nearly 2 decades. When Russian scientist Leonid Kulik led the first major expedition to the site in 1927, he arrived expecting to find a massive iron meteorite sitting inside a giant impact crater. Instead, Kulik found a strange butterfly-shaped pattern of destruction. At the very center, the trees were still standing upright, stripped of their branches like bare telegraph poles, and there was no impact crater to be found. A kinetic event with the force of 1,000 atomic bombs had occurred, yet it left no crater and no large rock fragments in the soil. In the absence of physical evidence, alternative theories filled the vacuum. These ranged from early science fiction stories about exploding alien spacecraft to rumors that inventor Nikola Tesla had caused the blast during a wireless energy experiment. The missing debris forced researchers to completely revise their existing models of how high-velocity cosmic bodies interact with the atmosphere. In 1930, British meteorologist F.J.W. Whipple proposed that the object was a comet. Because comets are composed of ice and dust, one would vaporize upon entry, explaining the lack of a crater and the glowing, bright nights reported over Europe. Modern astrophysics challenges this idea. A fragile, icy body would likely disintegrate too high in the atmosphere to cause the specific, localized patterns of damage found on the Siberian forest floor. Another theory, proposed by Wolfgang Kundt in 2001, looks below the surface. He suggested that 10 million tons of natural gas erupted from the Earth's crust and ignited in the sky, creating a massive aerial explosion. However, this geological explanation conflicts with the historical evidence. Eyewitnesses consistently reported a fiery object descending from space, rather than a gas cloud erupting from the ground. Neither fragile ice nor terrestrial gas accounts for every physical detail, leaving a dense, rocky body as the most consistent explanation for the evidence. Current scientific consensus, supported by complex orbital modeling, identifies the object as a dense, stony asteroid, roughly 70 meters in diameter. When a solid rock enters the atmosphere at 60,000 miles per hour, it generates immense ram pressure. The air in front of the object compresses so rapidly that the resulting heat and friction become overwhelming. This pressure causes the asteroid to violently detonate 5 miles above the surface. This airburst functions like a mid-air bomb, casting a shockwave downward without ever touching the dirt. This explains the blast pattern and the upright trees, but researchers still struggle to explain why no microscopic fragments of the rock were ever recovered. A 2020 study suggests the asteroid entered at a very shallow angle. It penetrated the atmosphere just enough to trigger the devastating shockwave, then skipped off the atmosphere like a stone on water. If this glancing blow occurred, the original Tunguska asteroid survived the encounter and is likely still out there orbiting the Sun today. The solution to the mystery was found by analyzing the fluid dynamics of our atmosphere. Tunguska demonstrates that an asteroid does not need to hit the ground to level a city. Our atmosphere acts as a physical barrier, capable of turning the kinetic energy of a relatively small rock into a massive nuclear-scale detonation. With millions of near-Earth objects still unmapped in the dark, constant astronomical monitoring remains our only defense against the next craterless blast.